Dear viewers, welcome to Source Tutorial. Today we are going to talk about the plastic method of structural analysis. Basically, we have, generally, we have two methods, which are equilibrium method or static method, and energy method or virtual work or kinematic method. So these are the two methods that are used in solving classic methods of structural analysis. So whenever you are asked to use any of these methods, you shouldn't be confused. If he asks you to make use of static method is the same as equilibrium method. Energy method, virtual work, or kinematic method are all the same. Now, I'll go straight to the example we have for today, and you're going to start with the energy method from this example. This example says that use the energy method to find the collapse load P equals to PC and the plastic moment MP for the prompt cantilever loaded as shown. So this is our prompt cantilever, where you have the load alpha P and P, which are loaded on the prompt cantilever, and the prompt cantilever has two supports, one fixed and the other roller, and the distances of the prompt cantilever from A to B is L over 3, B to C L over 3, and C to D is L over 3. Now let's go to the solution and let's know how to get the collapse load and the plastic moment for this prompt cantilever. Now, solution. We have this prompt cantilever as we have seen. Now, the first step, which is step one, to get the degree of indeterminacy of the structure. The degree of indeterminacy ID is equals to 2m plus r minus 2n. So this is a degree, the formula to get the degree of indeterminacy of any structure. But please be very careful, this is for cantilevers and beams. When we are going to talk about frames, it has its own degree of indeterminacy formula you use. Now let's go and get a degree of indeterminacy. ID is equals to, now what is our M? Let's get our M first. M means what? Number of members. What is a number of members? What is a member? In this cantilever, what is our member? Our member is member AD. This is a member. From A to D is one member. So here you have one member. Then R is the number of reactions. Now, how do you get your number of reactions? In getting your number of reactions, what you do first here is you ignore your horizontal reactions. While getting number of reactions. Now let's go to our prompt cantilever. In this prompt cantilever, here is a support, and this type of support is a roller support, and all roller support has one reaction, which is a vertical reaction which acts upward, which is RD. Then in this support B, which is a fixed support, it has three reactions. It has a horizontal reaction which acts upward, which is RA. It has a horizontal reaction, HA, and has what? A moment, MA. So these are the three reactions: the moment, the horizontal reaction, vertical reaction, and the horizontal reaction at this support. Whereas at this support D is only the vertical reaction already that is here. Now, excuse me. Now, let's count the number of reactions. Please, I said you ignore the horizontal. Let's count 1, 2, and 3. So we have 3 reactions, ignoring the horizontal reaction. Now, the next step to do is, next thing to do is to get your N. What is my N? N is my number of nodal points. My nodal points. What is a node? Let's go to our structure. This point A here is a node. Point D here is a node. So we have 1 and 2 nodes. So we have 2 nodes. Therefore, we say that our ID is equal to, so substituting this in this, we have 2. What is bracket? What is my M? My M is 1 plus my R is 3 minus 2. My N is what? My N is 2. So if we simplify, we have 2 plus 3 minus 4, which is equals to 1. Therefore, ID is equals to 1. Now the next step, find the number of hinges causing collapse. The number of hinges causing collapse will be equals to the degree of indeterminacy plus 1. So what is our ID? Our ID is 1 plus 1. Now, this number of hinges causing collapse tells us that my God. This number of hinges is equals to 2. That is to say that two hinges will be formed on our cantilever. That is, in this our cantilever here, in this cantilever, 2 hinges are going to be formed in this cantilever. Number of hinges causing collapse is equals to ID plus 1, which is equals to 1 plus 1, where since we have gotten our ID we have gotten is 1. So substituting this ID for 1 in this we have 1 plus 1, which is equals to 2. That is to say that the plastic hinges will be formed at A and B and at A and C. So let us show you where it's going to be formed at the cantilever. We said that it's going to be formed, that is, the plastic hinge will be formed at A and B and at A and C. Now, this is our prone cantilever. Now, this plastic hinge will be formed at this place, A and B, and also at E and C. And let me give you a hint how you know where the plastic hinge is going to be formed. So, in a prone cantilever or a beam, when you are solving, the way you know that a plastic hinge, or the place you will know where the plastic hinge is going to be formed, is where you have your maximum bending moment. Where a maximum bending moment will occur is that particular place, particular point where the plastic hinge is going to be formed. Now, let us go back to our pump cantilever. The example we have. Now, in this pump cantilever, remember, if you draw the bending moment diagram of this pump cantilever, remember here we have what? Two collapse load acting on a beam. So if you are drawing the bending moment diagram of this pump cantilever, it's going to be like this. At this joint, let me draw it this side. This is A, this is B. This is a fixed support, then this is our roller support. Then remember, if I'm drawing my bending moment diagram will go like this. Will be this way. If I'm considering alpha P, assuming one collapse load is being applied on this cantilever, on this prompt cantilever. So if I'm only assuming this, if I want to draw the bending moment, this is how it's going to look like. The bending moment is going to look like this. That is, there will be moment at this place, at this joint A, and there will be moment here. There will be moment here. Now, the plastic hinges will be formed at A and B. At A and B. Sorry, please. This is D. Sorry, not B. This is where our B is. This is where there will be a plastic hinge. The plastic hinge will always occur where you have what? A maximum moment. Where a maximum moment will occur at this support A, which is fixed, and at the region of what? At the region of the cantilever AD, at this region B. So it is at this point. So you have MP here. Remember, MP represents plastic moment. That is the plastic hinge represented by MP. MP here will be formed here, and also formed at this place, MP. So these are the two places where our plastic hinge is going to be formed. And also, you're going to have also a plastic hinge at A and C. A and C, that is at this place. At this place you have a moment. There will be a maximum moment occurring at this joint, at this support. There will be a maximum moment here, and also at this place. If I'm considering this load C, so if I'm considering load A, C, D, there will be maximum moment at A, at C only, and the places where the plastic moment is going to be formed is at A and at C. So if I'm considering this load alpha P, the plastic hinge is going to be formed at A and at B. That is to say, we have two mechanisms. We have the first mechanism we are going to have is mechanism AB and mechanism AC. So we are going to solve this using solve further by what the mechanisms we are having where our plastic hinge is going to be formed. Let's start our mechanism 1. Mechanism 1 means we are solving. Let me put this here. You can see. So now mechanism 1, we will solve. Okay, let me just write it. mechanism 1, considering a plastic hinge formed at A and B. Remember, a plastic hinge will be formed at A and B. Now, let's draw this mechanism. The mechanism will look this way. This is how our mechanism is going to look like. Now, in the first mechanism, they said at A and B. So, this is B, this is C, and this is my D, and this point is my A. Now, remember, when considering at B, that is maximum moment will be formed at this place. So, there will be moments here, So, then draw our plastic moment diagram. This is called the plastic moment diagram. Now, this angle is 2 theta, because this angle is 2 times this angle. So this angle is theta. This angle is theta. This angle is 2 theta. Why? Because if this angle is theta, then this angle will be 2. This one will be 2 times bigger than this one. Then the summation of these 2 angles will give us the external angle. So we have theta plus 2 theta is equals to 3 theta. Now, the next thing we do, we get our vertical displacement. What is our vertical displacement? Our vertical displacement will be called this symbol. So this is our vertical displacement. What is this our vertical displacement? Remember, we are considering A, B. So now, what is what is just like considering this angle AB? Let's call this point O. Consider triangle ABO. What is ABO? You find the opposite of this. Please, I'll go straight forward. To find this, multiply the length. What is the length here? Remember, the length here is L over 3. From E to B is L over 3. From B to C is L over 3. And from C to D is L over 3. From A to B is L over 3. So multiply the distance AB by the angle to get the vertical displacement of this side. So this times this angle will give you what? Will give you 2 theta L over 3. And what would be the vertical displacement of this one? Of this point C. The vertical displacement of this point C will be what? This, like from here to here, that is considering this triangle. Let me call this M. Consider triangle DCM. What is this side? This side is going to be the angle times the length, which is theta L over 3. Now, the next thing to do, you look for your internal, get your internal work done. The internal work done is equals to internal work done here is, that is, you go and add, that is, you add all the angles here, or add all the angles here. But in this case, remember that the natural range exists at, remember, the natural range exists at D. Now look at it. I told you earlier that in a prone cantilever, a natural range will always exist at this point, at this support. So a natural hinge is at this support. So no hinge is gonna be formed at this support. So when you are calculating the internal work done, you add up all the angles here, but this is not going to be added because a natural hinge does not exist. There is no natural hinge here, so the natural hinge exists already at this joint, at this point D. Then now, what is going to be our internal work done? Internal work done is going to be 2 theta MP plus 3 theta MP, which is equals to, you can still write this as 2 MP theta plus 3 MP theta, which is equals to 2 MP theta plus 3 MP theta will give me 5 MP theta. That is our internal work done. Then we get our external work done. Our external work done is equals to alpha P times the displacement. That is the workload times the displacement. Alpha P times the displacement. So give me alpha P times 2 theta L all over 3, which is our displacement, plus the load P times vertical displacement theta L all over 3, theta L all over 3. Now we multiply, we have 2 alpha P theta L all over 3 plus theta P L all over 3. Now we have our work equation. Our work equation is internal work done. Equate the internal work done to the external work done. Have internal work done equals to external work done. So equate it. So what is our internal work done? Our internal work done is 5 MP theta. We have 5 MP theta internal work done is going to be 5 MP theta, 5 MP theta is equals to our external work done is 2 alpha P theta L divided by 3 plus P theta L all over 3. Then remember, this theta goes off with this, so you are left with 5 MP equals to 2 alpha PL all over 3 plus PL all over 3 which is equals to 5mp is equals to, factorize out PL over 3, PL over 3. If I factorize out, I'll have PL over 3 all into 2 alpha plus 1. So from here, I'll make my PL subject of the equation. If I cross multiply, I'll have 15 MP is equal to PL into 2 alpha plus 1. So make P subject the formula. I'll divide both sides by what? P into 2 alpha plus 1. So have, L is L 2 alpha plus 1. So this goes with this goes with this. So we have P is equals to 15 MP all divided by L into 2 alpha plus 1. Therefore, we say that our load PC, critical load PC, is equals to 15 MP all by L into 2 alpha plus 1. Then what is our MP? Our MP, that is from here, I can get my MP or say 5 MP is equals to P all over 3 into 2 alpha plus 1. So my MP is going to be MP equals to that multiplying both sides by 1 over 5 by 1 over 5. Multiply both sides by 1 over 5. This 1 over 5 go over 1 over 5. Then you're left with MP. Then this 5 multiply this 3. You're left with PL all over 15 of 2 alpha plus 1. Therefore my MP is equals to PL all over 15 into 2 alpha plus 1. So this is my MP and this is my load. Peace.